So now we're going to talk about something called the triple scalar product. And we've actually seen it before. It was U dot V cross W. We saw this in the properties video. This is called the triple scalar product. And so now I want to talk about how to compute this. You could compute it kind of the long way, but there's this shortcut. So if you want to compute U dot V cross W, it's kind of, you compute it the same way as a cross product, but now instead of having I, J, and K in that first row, you're going to have the vector U, U1, U2, U3, and then you still have V1, V2, V3, and W1, W2, W3. And when you do this computation, you're going to get back a scalar, and it won't be a vector anymore. So one application of this triple scalar product is an object called a parallelepiped. So this is a three-dimensional object, and this is a polyhedron whose faces are parallelograms. And I'm not going to subject you to one of my horrible drawings of this object. You can Google it and probably find a good picture. What I think of it as being is, imagine you have a box, and then imagine that the sides are kind of flexible and you push the top part at an angle, and so all the sides now are parallelograms. And so there's this geometric property of the triple scalar product. And here's the property. It says that the volume of a parallelepiped with vectors U, V, and W as adjacent edges is the absolute value of this triple scalar product. So remember that this triple scalar product here, this is a scalar, and so we're not taking a magnitude, we're only taking an absolute value. And so these three vectors, I said I wasn't going to try to draw a picture, but I guess I am now. This is probably a horrible drawing, so please forgive me. Well, okay. I'm not going to go into too much detail, but let me draw the base here. And then you would have a side length coming up here. So again, that's a really rough scale picture, but you have U as being one of these here. V as being this other side length here. And then W would go up and then W would be like this one here. UV, and then that would be the vector W. They need to be the adjacent edges. All right, so let's look at a problem here where I have to try to find this volume. Let's look at this example. Find the volume of the parallelepiped having these vectors as adjacent sides. So u will be 3i minus 5j plus k. V will be 2j minus 2k. And w will be 3i plus j plus k. All right, so to find this volume, we take the absolute value of this triple scalar product. So I'm going to start by finding this triple scalar product, u dot v cross w. So you take and write the vector u first, 3, negative 5, 1. The vector v has no I, so it'll be 0, 2, negative 2. And then 3, 1, 1. You compute this just like you did when you had an I, j, and a k here. So it'll be 3. And then you remove the first row and first column, 2, negative 2, 1, 1, minus, now you have a negative 5. Remove the first row and the second column, 0, negative 2, 3, 1, plus 1, and now you'll remove the first row and the third column, 0, 2, 3, 1. So now we're going to compute this. Let's see, 3 is 2 minus a negative 2, so plus 2. That's a positive 5 times 0 minus a negative 6, so 0 plus 6 plus 0 minus 6. So here, if you add all these up, you should get 36. So the volume would be the absolute value of 36, which is just 36, and that's my volume of this object.